So part two, take two, no. We're going to be talking about the mole today, and this is not the mole we're talking about. This is a creature that you don't want in your garden. Although he's got awesome hands. Don't you wish you had hands like that? I wish I had hands like that. Oh, whoops, no, not that mole either. Oh my gosh, Mr. Alley, you're so weird. No, we're not talking about that mole either. We're talking about a different kind of mole. Go ahead and take a moment and write that down, and I'll be right with you. Okay, so in chemistry is very measurement dependent. As you are doing chemistry, you've got to know how much of this thing and how much of this thing are reacting to make how much of something else, right? And so here in the room, we weigh things with scales. We've got flasks and graduated cylinders for measuring volumes. And there's all kinds of ways of taking a measurement. But when you take a measurement of a liquid, let's say you've got 5 mils of something, you know you have 5 milliliters of that. But how many molecules of the liquid does that 5 milliliters represent? Well, you don't really know. And if you're going to be reacting something with something else, and you need to be very careful that it all reacts. And so you know you don't have any leftovers of one or the other. You need to know how many molecules of this substance you have and how many molecules of the other substance you have so that you're reacting a one-to-one relationship and they all react, they all go away. So before the work of this guy, Amedeo Avogadro, I love that his name both alliterates and rhymes. I think that's cool. Amedeo Avogadro, like a rapper should make a song about that. Anyway, Amedeo Avogadro discovered felt the need to know not just that I have so many grams of something or that I have so many milliliters of something, but that I have so many atoms or molecules of something. How many actual molecules does this represent? So he started to work out a way of measuring the number of atoms or the number of molecules of a substance. And he came up with a number called Avogadro's number, named after him. And actually, he did a lot of work on it, but he himself did not finish the project. He didn't wind up coming up with the number. He died before he was done with his work. But when the work was completed by later scientists, they named it after him because he began the questioning along these lines. So Avogadro's number is 6.022 times 10 to the 23rd of something. And we call that the mole. How we got it to be called the mole, I don't know. It's not named after the skin blemish, and it's not named after the burrowing rodent. So I don't know exactly why it became known as the mole. It's probably an abbreviated Latin word for something else. But we call it the mole. And when you have a mole of something, you have this many of those things. 6.022 times 10 to the 23rd is a stupidly large number. If you write it out, it's this. So these are hundreds, these are thousands, these are millions, these are billions, these are trillions. And if we are Americans, we just keep adding a Greek prefix. So trillions, quadrillions, quintillions, hexatillions. So 602 hexatillion, 200 quintillion of something. You can't comprehend that big of a number. That means nothing to you because we don't. Nobody has this many of something. You can't sit down and be like, oh, that's how many dollars I have. No. That's how many people on the planet. No, not at all. That's how many grains of sand on a beach, possibly. But wow, we don't have any idea how much that is either. So this is a really, really big number. If you were to try to grasp the concept of a mole, of how many things a mole is, it's just, it defies logic. Your brain starts to explode. So let's help you here. 1 mole of seconds is 19, what is that, 100,000 million, billion, trillion, 19 quadrillion years would be a mole of seconds. Yeah, it's too big even. You're like 19 quadrillion years. Even the oldest old Earth scientists who think that the universe is really, really old only go to 4.5 billion, or sorry, 18 billion years. So 18 billion is, way down. My mouse does not want to work. way down here. And we've got all that more to go. So no, that doesn't really help. 1 mole of dimes, let's picture a mole of dimes, stack up on top of each other, would reach from the Earth to the Moon over 2 trillion times. That doesn't really help you either. From here to the Moon is a long ways away for a stack of dimes, and then imagine that you could do that 2 trillion times with a mole of dimes. A mole is a really, really big number. 1 mole of atoms of carbon, though, weigh 12 grams. And that's where we got the mole. Is, if you look at the periodic table, carbon has an atomic mass of 12. And so there are 6 protons and 6 neutrons. So a carbon has an atomic mass unit of 12. Well, Avogadro said, okay, it has an atomic mass unit of 12. How many carbon atoms do I need to have weigh exactly 12 grams? So that was his life's work, was that question. How many atoms of carbon weigh 12 grams? So that he could get the conversion between an atomic mass unit and the metric system. And so his life's work was to count atoms, right? And you can't, atoms are too small. You can't like take your scalpel and go 1, 2, 3, 4, 5. You can't do that. So you have to do it by weighing fractions and looking for, yeah, it's a very, very complicated process. And he spent his whole life asking the question, how many atoms of carbon weigh 12 grams? And later on the answer was done by later scientists, and it was named after him, and that's where we get the mole, right? So 6.022 times 10 to the 23rd atoms of carbon weigh 12 grams, and we have now used this as the math bridge for us between how much something weighs and how many atoms or molecules of that thing there are. Okay? So, take a moment and write that down. Okay, so I already said it, and now you've got a chance to write it down. Avogadro's number is the number of pieces of something. It can be atoms, it can be molecules. The number of pieces of something that you have to have so that its atomic mass unit number equals its mass in grams. So when we were talking about the periodic table, when we talked about the atomic weight of things, you were comfortable with the concept of an atomic mass, right? Helium has an atomic mass of 2 because it has 2 protons. I'm sorry, it has 4 because it has 2 protons and 2 neutrons. So it has an atomic mass of 4. Carbon has an atomic mass of 12, 6 protons, 6 neutrons. But when you drop a carbon atom on a scale, it doesn't weigh 12 grams. So the concept of an atomic mass unit is kind of, I don't know, abstract. You're just counting the numbers of things in the nucleus. But that doesn't give you a direct weight. It's just the number of things there, right? And so the mole, Avogadro's number, the mole is a way of bridging the number of things that I count in the nucleus of the atom with how much it weighs. So in order for carbon, which has an atomic mass unit of 12, to actually weigh 12 grams, I have to have a mole of carbon atoms for it to actually have that weight, for them to come together and mean the same thing. So that allows me to weigh a mass of a sample and know how much a mole of that thing weighs based on the periodic table, and then determine how many actual atoms of this substance do I have, or how many actual molecules of this substance do I have. Okay? So, molar mass, that phrase molar mass, is the amount of mass 1 mole of a substance has. So for an atom, it's really easy. It's the atomic mass unit. Carbon has an atomic mass unit of 12, 6 protons, 6 neutrons, an atomic mass unit of 12, which means that if you have a mole of carbon atoms, you have 12 grams. But we don't usually work with just a single kind of atom. Most things are not elements. Most things are a compound. There are multiple atoms bound together. So if I want to know what does a mole of water weigh, well, I can't just look at the periodic table because there's no field on the periodic table for water. It's a compound. So I need to determine the molar mass of water and figure out what does a mole of water weigh. I can add up the molar masses for each of the elements in that compound and determine the molar mass of the compound. So if I want to know what does a mole of water molecules weigh, well, the molar mass of hydrogen is 1, and I'm just being simplistic right now. It's actually 1.00 something, right? But we're going to just, for the ease of this example, call it 1. And oxygen's mass on the periodic table is 16. So what's the molar mass of water? It's 2 hydrogens and an oxygen. 1 plus 1 plus 16 is 18. So if I had 6.022 times 10 to the 23rd molecules of water, those molecules of water would weigh 18 grams. Or I could go do it the other way around. I could very carefully weigh out 18 grams of water. And if my scale were really precise, and I had a high degree of confidence in my measuring skill, and I got the scale to read 18 exactly, then I would say in that container there is 6.022 times 10 to the 23rd molecules of water. Because Avogadro's number, the mole, is the number of molecules you have to have for its weight to equal its atomic mass unit number, the sum of the atomic mass unit numbers. Do you understand the concept so far? It's the number of things that weigh this much. Okay? So you look at the periodic table and the atomic mass numbers for whatever compound you're looking at, you add up the atomic mass numbers for that molecule, and that will, the atomic mass number, the sum of them, will equal the mass of 1 mole of that compound. Do you guys understand so far? Okay. So let's do an example problem. Quartz, this crystal, is silicon dioxide. Okay, that's the chemical formula for quartz. Silicon has an atomic mass unit, an atomic mass number of 28.09 mass units. Okay, oxygen is 16.00 atomic mass units. So if I wanted to determine what is the molar mass of quartz crystal of silicon dioxide, I would say 28.09 grams for the silicon, right? And there are 2 atoms of oxygen for every 1 atom of silicon. So I have to have 2 times the atomic mass unit number for oxygen. So the sum would be 28.09 plus 32 is 60.09 grams. 1 mole of quartz crystals has a mass of 60.09 grams. If I have 1 mole of silicon dioxide, then that many 6.022 times 10 to the 23rd molecules of SiO2. If I were to have exactly that many molecules of SiO2 in a bucket, and I weighed it, it would weigh 60.09 grams. So again, the mole is a bridge between how many of these things do I have and how much does it weigh. Okay. Now I could ask the question the other way. I could say how many moles of quartz are represented by 124.6 grams of a pure sample. This is more likely the way you're going to use this. I have this much quartz crystal. How many molecules of quartz do I have? So 124.6 grams. If I already know, I've got to move my picture all around now. If I already know that the molar mass is 60.09 grams and I have 124.6 grams of this, then I can set up a ratio here that 1 mole is 60.09 grams, right? And so 124.6 grams of something times my conversion factor, I've got to have grams cancel, grams and grams. They're going to cancel. And so I multiply across 124.6 divided by 60.09, and I'm going to be able to tell that I have 2.073556 moles of quartz crystals, but I've got to watch my significant digits. So I gave myself 4 significant digits in the measurement, and I have 4 significant digits in my AMU number here, my molar mass. So I can use 4 significant digits in the answer, 2.074 moles. So if I have this much pure quartz crystal, I have this many moles of molecules. I have this many times 6.023 times 10 to the 23rd molecules of it, right? A mole is like a cup or a measuring unit that you can use for all kinds of things. So I have this many moles of molecules of quartz. Do you understand that example? I think I have another one, but do you understand this? Do you understand this idea? Okay. Alrighty, so percent composition. Take a moment and write that down. So percent comp. This is the other concept from this section of the textbook. We're going to be looking at more masses and asking how much of this molecule is made up of a particular atom. Okay, so this molecule has tons of different atoms in it. What percentage by weight is this atom of this compound? So what percentage of compound X is atom Y? And the example I gave here is how much of the mass of water is given to it by hydrogen. Water is H2O. Each hydrogen atom has a weight of 1. So 2 hydrogen atoms, 2 times 1, the hydrogen atoms together weigh 2 mass units, right? And so of the 18 that is water, 2 of that is hydrogen. So 2 divided by 18 gives us 0.111, or about 11%. This is something that you're going to use a lot in chapters 9 and 10, and then sporadically throughout the rest of chemistry. But it is something that you definitely have to have a grip on to move forward. So we need to be able to it's just simple division. None of this is hard math, right? But it is math. You need to be able to look at a periodic table, add up all of the mass units of a compound, and then determine how much of its weight is made up by a particular atom that's in that compound. Okay, do you understand the idea? Okay, so Cody, part of Cody's weight right now is his shoes, right? His shoes make up part of his mass. If I wanted to add up how much of the mass of Cody right now is composed of his shoes, I could add up, Cody's hair, plus Cody's eyes, plus Cody's head, plus Cody's sweater, plus his pants and his socks and his shoes, and I can have components for all of these, and I can determine of his weight right now, his shoes are make up a certain percentage of his weight. It's the same idea here. How much of the weight of this molecule is composed by a particular atom within it. Okay? Here's how you use this. You use percent comps to determine formulas. So if we were to have some unknown molecular structure, I don't know what's in this thing. It's a mystery to me. But when I break the thing up, I determine that it has a certain percentage composition of hydrogen and carbon. Then I could go back to their masses and say it's this percentage hydrogen, this percentage carbon, and I can come up with the structural formula if I know the percent compositions. So you don't very frequently go, here's the formula, what's the percent composition? You more frequently say, here's the percent composition, what's its formula? I've put these things together and they made a molecule. What did they make? And so if I were to, in this example here, if a substance is determined to be 20% hydrogen and 80% carbon, using the molar masses will let you determine that the formula is H4. So carbon is 16 on the periodic table, its atomic mass unit is 16. Hydrogen has 1 atomic mass unit. So if I'm going to stick carbon and hydrogen together in such a way that 80% of its mass is made up of carbon and 20% of its mass is made up of hydrogen, I've got to find a way to combine 16 and 1 so that it's an 80-20 ratio. And I could determine that 4 hydrogens would have a mass of 4. 1 carbon has a mass of 16. And the relationship of 4 and 16 is an 80% to 20% relationship. So I would say, oh, I have to stick 4 hydrogens onto 1 carbon to make this ratio that I determined experimentally exists. There's an 80-20 relationship, hydrogen-carbon. I have to then figure out that I have the formula of CH4. Okay, so this is how you're going to actually use this in your math problems in chapters 9 and 10, is looking at a percent comp that's given to you and determining what is the structural formula of the substance. Okay, and so you'll have to play with the masses until they have that right relationship. 4 times 1 is 16. 4 times 1 is 4, plus 16 is 20. 4 is 20% of 20, and 16 is 80% of 20. So I have a 20 and 80 relationship. Do you see how this happened? Okay, so in real chemistry, if somebody gives you an unknown sample and you find something, you don't know what it is, one of the ways of determining what the sample is to break it up into its component elements, weigh how much of the elements you have, and then say it's these percentages. Let's use those percentages to go back and determine the structural formula of the thing that I was given. So here's an example problem. Analysis of an unknown substance shows a composition 15.87% carbon, 2.22% hydrogen, 18.50% nitrogen, 63.41% oxygen. What is the empirical formula? What is the formula of this thing that I've been given? So I need to come up with an imaginary mass of this substance. How do you do it? If I'm going to say, let's say I've got 100 grams of this substance, and it's helpful to always come up with an imaginary sample of 100 grams, because then the percentages become masses. So let's say I have 100 grams of this imaginary substance. 15.87% of it is carbon. Well, 15.87% of 100 grams is 15.87 grams of carbon. So I just turned my percentage into a mass. 2.22 grams of it then would be hydrogen, because the percentage becomes grams. 18.50 grams of it is nitrogen. 63.41 grams of it is now oxygen. So I have turned my percentage compositions into weight by multiplying that percentage by 100 grams. So now I have this many grams of these things. How many moles of that do I have? Well, carbon has an atomic mass of 12. So 15.87 grams of carbon divided by 12 grams per mole gives me 1.3225 moles of carbon. This is the kind of example that we did in the first part of the problem. So I have a mass of something, and I know its atomic weight, and so using the concept of a mole, I can divide the number of grams by its molar weight and get the number of moles, how many molecules of carbon I have. Sorry, how many atoms of carbon I have. Do the same thing for hydrogen. Hydrogen has 1 atomic mass unit as the weight of a mole, of an atom of hydrogen. So 22.22 divided by 1 is 2.22 moles of hydrogen. Repeating for nitrogen, this is the molar mass of nitrogen, 14.01. I have 18.5 grams of it. 18.5 divided by 14.01, I have 1.3205 moles of nitrogen. Do the same thing for oxygen. So I wind up having 3.963125 moles of oxygen. So in my imaginary sample of 100 grams of this unknown substance, I've determined that I have a certain number of moles of atoms. This becomes very helpful because I don't know my formula yet, but now I know my molar ratio. Now I know how many moles of these various things I have to each other. Do you see 2 numbers up here that look very much like each other? Carbon and nitrogen. So I could look at this and say I have about a 1-to-1 relationship of carbons to nitrogens. It's not exactly the right number because somewhere in here my measurements are not perfect, but it's approximately a 1-to-1 relationship of carbon and nitrogen. So whatever I have, it has an atom of nitrogen for every atom of carbon. And then you can see as well a very close multiplier. I could get the number of carbons to hydrogens and the number of carbons or nitrogens to oxygens. If I were to look at the ratio of these numbers, 1.3 to 1.3, that's about 1-to-1. 1.3 to 1 to 2.2, it's not perfectly a 1-to-2 relationship, but it's pretty darn close, right? So what I need to do is divide all the moles by the smallest number to get the molar ratio. And examples like this are given to you in your book. But my smallest number is 1.3205. I'm going to divide all of these numbers by my smallest number. And I'm going to get about 1.5-ish, 1, and 3. Okay? Now, these aren't perfect integers because I'm working with approximate numbers here and I had to round all of these numbers. So, but approximately 1, 1.5, 1, and 3. So I could build a formula now with how many of these atoms I have in a substance. And I could do that with 1 atom of carbon, 1 atom of nitrogen, 3 atoms of oxygen. But I can't have 1.5-ish atoms of hydrogen. How am I going to solve this problem? Yeah. Double everything. Perfect. So if I double all of these, then I have 2 atoms of carbon, 3 atoms of hydrogen, 2 atoms of nitrogen, and 6 atoms of oxygen. So the best way to get whole numbers, right? And I said here, since hydrogen is about 1.5, multiplying everything by 2 and rounding slightly gives me whole numbers. And I wind up with C2, H3, N2, O6. And so if I don't know the formula, but I do know the percent compositions, doing some math and using some logic, I can determine that what I've been handed is C2H3, N2O6. Now I don't know how that is put together. I don't have a structural formula yet. I don't have like this meets with this in this way. But now I could draw a Lewis structure and I could determine molecular geometry off of my Lewis structure. Okay? And so that's the kind of stuff we're doing in chapters 9 and 10. You will get a ton of practice with this, both in the lab tomorrow and in the lab Thursday, Friday, and those of you who dual enrollment doing the chapter section review questions. All right? So that is the kind of stuff we're doing. Questions? Okay. Yay, math. Now you're ready to do Lewis structures and see if you can figure out how it fits together. There you go. That's it. Okay. Thank you very much. You are done with this lecture, yes.
Can I give you my lab?